Welcome, everyone, and thank you for joining today's session on modern web performance and linguistics. In this presentation, titled Hangul WASM, Deconstructing the Architecture of Korean Text Processing, we will conduct a deep dive into the intersection of low-level system architecture and complex script handling. Our focus today is on system architecture and logic analysis. We will explore how the unique modular structure of the Hangul script can be efficiently processed using the high-performance capabilities of WebAssembly. By breaking down the underlying logic of character composition and decomposition, we can understand how to build faster, more robust text engines for the modern web. Let's begin by examining the core architectural framework that makes this integration possible. The intersection of linguistics and binary performance explores the optimization of complex string manipulation using WebAssembly. By migrating the logic of Hangul processing from standard JavaScript to a compiled WASM module, we achieve near-native performance for decomposition and composition tasks directly within the browser. This approach allows us to bridge the gap between complex linguistic rules and high-efficiency computation, ultimately enabling real-time synthesis. Hangul is not written linearly, rather it is built architecturally. Unlike the Latin alphabet, where letters follow one another sequentially, Hangul groups its individual components, known as jamo, into distinct syllabic blocks. Each character serves as a container defined by specific spatial coordinates. Examining the anatomy of a syllable using the character han, we can see this structural logic in action. The block is divided into three key roles: the chosung, or initial consonant, the jungsung, which serves as the central vowel nucleus, and the jungsung, the final consonant that anchors the base of the block. This multi-dimensional arrangement transforms individual phonetic markers into unified architectural graphic units. Decomposition is the process of extracting the atomic components of a language's script. Specifically, the decompose function takes a unified syllabic block and breaks it down into its constituent jama sequences. By taking a character block and processing it, we can isolate the initial jama, medial jama, and final jama as distinct data points. This granular approach is foundational for several core technical applications. In search indexing, it facilitates the normalization of text for more efficient database storage. For fuzzy matching, it enables advanced search capabilities, such as finding results based on initial consonants. Finally, it serves as a critical step in morphological analysis, providing the necessary pre-processing for complex natural language processing tasks. Composition synthesizes input into readable text by utilizing a specific compose function. This function is responsible for stacking atomic jamo, the building blocks of the Korean script, into correct Unicode syllables. As illustrated, individual components are processed through a dynamic input system that powers modern Korean keyboards. This mechanism does more than just assemble characters. It facilitates autocomplete through predictive text completion and manages correction by automatically merging orphaned vowels and consonants. The final result, as shown with the syllable han, demonstrates a seamless transition from raw input to finished, structurally accurate text. When we examine the computational cost of string manipulation, we must acknowledge that while JavaScript is highly optimized, high-frequency text processing on large datasets introduces measurable latency. Handling Unicode logic at the byte level creates significant overhead, which directly compromises UI snappiness and overall responsiveness. As illustrated by the graph, there is a nonlinear relationship between data volume and latency. While simple text operations remain relatively efficient, complex processing requirements cause latency to spike sharply as the volume of data grows. Understanding this curve is essential for optimizing performance in data-heavy applications. WebAssembly is revolutionizing the digital landscape by bringing native performance directly to the web. It serves as a binary instruction format that runs in parallel with JavaScript, providing a robust foundation for modern applications. By allowing low-level languages such as Rust and C++ to operate within the browser at near-native speeds, it effectively acts as a turbocharger for computationally intensive tasks. This capability opens new doors for complex software to run seamlessly in a web environment without sacrificing performance. The Hangul.js architecture is designed as a hybrid system that bridges a flexible front-end with a high-performance back-end. On the left, the JavaScript context manages dynamic operations such as event handling, DOM rendering, and user input, ensuring a responsive interface.
On the right, the WebAssembly module serves as the specialized engine for performance-heavy tasks, including Unicode logic, memory management, and complex binary calculations. By facilitating communication through a dedicated binary interface, this implementation combines the versatility of JavaScript with the efficiency and speed of compiled binary code.
Tracing the data path from input to output involves several distinct stages of memory management and execution. It begins with the input string, which represents the raw data provided to the system. To bridge the gap between the host environment and WebAssembly, this data is written into a buffer within the memory heap. Once the information is securely stored in linear memory, WASM execution commences, where the module performs its defined logic on the input. Upon completion, the module does not return the actual result directly. Instead, it provides a pointer return, which points to a specific memory address in the heap. In the final stage, the host environment reads from this location to perform data extraction, transforming the memory-stored result back into a usable output format. When addressing performance implications at scale, we focus on three core areas: reduced latency, battery efficiency, and predictability. First, by prioritizing reduced latency, we ensure immediate feedback loops for the user, maintaining high responsiveness even when dealing with massive text blocks. Second, battery efficiency is optimized through the use of compiled binary code, which performs tasks using significantly fewer CPU cycles. Finally, we provide predictability by ensuring consistent execution times that remain independent of JavaScript engine variants. Together, these factors deliver a high-performance, reliable experience for users at any scale. Our focus now shifts to the demo for instantaneous synthesis. This proof-of-concept environment illustrates a system where text is simultaneously decomposed and recomposed. In the decomposed view on the left, we see individual character components isolated, while the composed view on the right displays the final, structured output. The core innovation here is the synchronization between these two states. As elements are modified or analyzed, the system updates across both views with zero perceptible delay, providing a truly fluid and responsive experience. Abstraction is a fundamental principle that preserves developer simplicity. In this architecture, while the WebAssembly backend manages complex tasks such as memory allocation and low-level processing, the external interface remains incredibly straightforward. As shown in the code example, a developer only needs to call a single declarative method, decompose, to process a string. The intricate logic required to break down Hangul characters into their constituent components is entirely encapsulated. This ensures that the JavaScript API remains clean and easy to integrate, allowing developers to leverage high-performance WASM capabilities without needing to manage the underlying complexity. The capabilities of a WASM engine extend far beyond simple demonstrations, enabling sophisticated applications directly within the web browser. For instance, in the field of text editing, it facilitates the creation of robust, web-based word processors with near-native performance. In the context of search engines, it allows for efficient client-side indexing, enhancing both responsiveness and data privacy. Furthermore, it plays a critical role in AI preprocessing by enabling the tokenization of large datasets locally in browser, which streamlines workflows and reduces server dependency. The landscape of browser-based linguistics is undergoing a fundamental shift. Currently, most advanced language processing relies on remote servers, but we are moving toward a future where heavy linguistic tasks, including grammar correction, translation, and semantic analysis, are handled entirely on the client's device. This transition, illustrated by the progression from our current limited capabilities to a broad horizon of client-side intelligence, is driven by the critical need for enhanced user privacy and robust offline functionality. By shifting these complex computations to local hardware, we can provide users with linguistic tools that are faster, more secure, and accessible regardless of their internet connectivity. The Hangul.js WebAssembly integration represents a profound synergy between linguistic theory and modern software architecture. It is, at its core, a study in structure. By mirroring the inherent nature of the Korean language, our system constructs complex meaning from fundamental atomic units with unwavering mathematical precision. This approach allows us to translate the modular elegance of Hangul into a high-performance digital environment, ensuring that the logic of the script is perfectly preserved within the efficiency of WASM.